So for today, we are going to be going over the properties of compounds, the properties of ionic compounds, the properties of molecular compounds, acids and bases and things like that. Okay, we are going to be focused primarily on physical properties. Okay, so what would I be talking about if I was talking about the physical properties of something? What would be some physical properties?
Certain traits of it has horns or how many legs.
Okay, yes. Okay, if we're talking about animals, yes. How many legs or horns, okay, would be physical properties. If we're talking about chemical compounds, what would be physical properties? And it goes along the same line. These are something that we can see and describe about the chemical. What would be physical properties of a material? Here.
The color.
Color, absolutely. Okay. What else? Eric's figured it out because he saw it in the next page of the notes already. What else?
Density.
Density, melting point, boiling point, solubility, okay, things like that. They are all pH. Okay, whether the solution can conduct electricity, we call that aqueous conductivity. Whether this material is magnetic, okay, or not. Right? All of those kind of things. Those are all physical properties. They are things that are inherent to that material. Right? Now, some materials share lots of physical properties, but there's always something about each material that makes it just a little bit different from the next. Okay, does everyone kind of follow me on that? Okay, where we're headed with this is in our lab on Monday. What we want to be able to do is use the physical properties of about a dozen unknown materials. We want to use the physical properties of those unknown materials to identify them from a list. Okay, so the lab will work like this. On the front table of the lab will be, I think it's 12, unknown materials labeled A through J, whatever the 12 letters, something like that. Okay? They'll just be labeled with letters. And you'll have a list of their possible identities. And what you're going to have to do is measure, record, okay, the physical properties of each one of those unknowns, and then match it up with one of the names. Okay, so for example, one of the unknowns is going to be distilled water. Okay? Now, what are the physical properties of distilled water? What color is water? It's clear. Okay, so it's transparent. What state will it be in at room temperature? It'll be a liquid. Okay? What's its pH? 7, right, it's neutral. Okay? Does distilled water conduct electricity? No, it doesn't. Okay? If I added more water to it, would it dissolve? Okay, would it mix together and not have two visible parts? Yes, that's what I mean by dissolve. You can actually, liquids can dissolve in other liquids. Just means that they basically are soluble and they absorb it. Okay, so those are easy physical properties of water. If I had an unknown that was a clear liquid with no smell, okay, that had a pH of 7, didn't conduct electricity, I'd say that was probably water. Now, if I had another clear liquid that also was obviously liquid, clear, and dissolved with water, did all those things, but had a strong odor, would it be water? What if it smelled like hand sanitizer? What might it be? What's in hand sanitizer? Alcohol. Yeah. Okay. If I had just pure alcohol, okay, then I would have something that had basically all the same physical properties as water, except it smells, and water doesn't. And that would be how I would tell them apart. Okay? They're both molecular compounds, okay? So a lot of their physical properties are shared, but they have this one thing that makes them different from each other. Now, obviously they'd have different melting points and boiling points as well, but we're not testing that. It's not something we can accurately test. Okay? Everyone kind of follow?
Can we use the washroom?
Yes. All right, so that's what we're going to be looking at. We're going to be looking at the properties of ionic and molecular compounds today. You're going to need to add a few things to your notes package today because I'm going to give you a few kind of key identifying characteristics for some of the things that we're going to go over in the lab or have to identify in the lab, so it'll be helpful when you're doing your analysis. So if I say make sure you write this down or add this, make sure you do. Okay? All right, so all material has certain properties. Some are chemical properties. We're not dealing with chemical properties today. Chemical properties are things like reactivity. So if I drop a chunk of sodium in water, basically it explodes. Okay, that's reactivity. It's highly reactive. Oxygen is highly reactive with basically everything. Okay, we're not testing chemical properties. Okay, and then there are physical properties: color, density, melting point, all the things we just talked about. Those properties can be used to distinguish between different types of compounds: ionic compounds and molecular compounds, and then individual compounds within the subsets of ionic and molecular. Okay, so here's some things we need to know about ionic compounds that will help us in our lab. Ionic compounds typically exist as crystalline solids or salts at room temperature. Okay, so when we use the term salt, we're usually talking about like table salt, okay, or salt we would add to food. But the term salt is actually a general term that applies to all ionic compounds. Anything that is a solid containing a metal and a nonmetal is technically a salt. It's not salt like you would use on your food. Some of those salts would be highly poisonous or taste really bad. Okay, but obviously table salt, sodium chloride, is an ionic compound. Okay, but all ionic compounds are typically going to be crystalline solids at room temperature. Each ionic compound's crystals are a little bit different. Okay, now that's not something we can really see well. There are some that are obvious, but there are some that are less obvious. Okay, they all have different melting points, but their melting points are all very high. Ionic compounds typically don't start to melt until they're several hundred degrees. Okay? And one of the other things they do is when you add them to a solution, they usually dissolve easily. Ionic compounds are usually highly soluble. There are exceptions. And when they dissolve, the solution they make will conduct electricity. Okay? So tap water conducts electricity. Okay? But tap water contains lots of ions in it. Contains calcium, contains chlorine, okay? Contains fluoride if you live in a place where they put that in the water. Okay? Things like that. It's always got stuff dissolved in it. And we know that because it's the stuff that deposits out on the side of your shower. Or if you accidentally boil off all the water in a pan, it's the stuff that burns onto the bottom. It's all the minerals that are in the water. Okay? Distilled water, on the other hand, has nothing in it. It's just pure water. So it doesn't conduct electricity because water is a molecular compound. Okay? Everybody with me so far? So one of the tests that you're going to do in your lab is a conductivity test. So you'll have a solution. You never test the solids. Okay? Like you don't just stick this in a crystalline solid and go, oh, does it conduct electricity? Because it won't. Okay? You have to make the solution first. So this is just demineralized water. It's not perfectly distilled water, so it'll probably conduct electricity a little bit. Okay? But if I put my conductivity tester in there, incidentally, you will be using these. Okay? They're very easy to use. They have a button on the side, and then they have a light that tells you if it's actually working. Okay? So I press the button and the red light comes on. Okay? If I put this in the water, you can see the conductivity is 1. So it's basically non-conductive. All right? That's what distilled water would typically look like. Now, if I add just a little bit of table salt, now it's up to 7. Actually, if I stir it even more, it'll probably go even higher. Okay, did it change considerably? Right, and all I did was add salt. Now, why does that make it conduct electricity? Because we talked about the structure of ionic compounds the other day, and we said that when they hit water, they split apart. Okay, we call that dissociate. Okay, so they dissociate with each other, and they become individual charged particles called ions. This would be a sodium ion. It would be floating around in that water. Okay, a chlorine ion that would be negatively charged, floating around in the water. Because there's charged particles in the water, electrons can flow between them, and the material, the solution, then conducts electricity. If I have just pure water, there are no ions in it, and the electrons can't jump from one particle to another because there's no charged particles to trade. Right, all right with that? Okay, that is the one test that will always tell you whether a material is ionic or molecular. You might want to write that down. Okay? Ionic compounds conduct electricity in solution. Molecular do not. That is the one test that will always tell them apart. Now, on Monday, one of your unknown compounds is sodium chloride, table salt. And another one of your unknown compounds is sugar. Because they look a lot alike. Yeah, they're both white crystalline solids. Okay, their crystals are slightly different in shape, but it's pretty hard to tell just at kind of the visual level. Okay, they don't really, I mean, there's maybe a slight smell difference, but unless you're really familiar with what salt and sugar smell like, okay, and they don't have much of a smell at all, okay, you really wouldn't be able to tell them apart. But salt is ionic, sugar is ionic or molecular? Okay. Carbon, metal or non-metal? Non-metal. Okay. Hydrogen listed second, non-metal. Oxygen, non-metal. All non-metals, this is molecular. Okay, so if I've got two white crystalline solids, I know one of them is sugar and one of them is salt, and that's the situation you're going to be in on Monday, okay? The way I could tell them apart is salt solution will conduct electricity, sugar won't. Okay? When I put sugar in water, it dissolves, but it doesn't dissociate. Okay? There are no charged particles, so a solution of sugar water would not conduct electricity because it's a molecular compound, not an ionic compound. Okay? Now I did hear somebody say you could taste it. The problem with that is there are a couple of other white crystalline solids, and if you taste them, it will be the last thing you ever taste. So there will be no taste testing in the lab. Simply because, you know, I don't want you to have like a chemical tracheotomy. Okay, because you know, you drink an acid and it burns a hole in the throat. That'd be bad. So no taste tests in the lab. All right, so we said ionic compounds typically exist as crystalline solids. They have high melting points. Ionic compounds will conduct electricity when they're in solution, and that's because of the nature of the positive and negative ions that make them up. Okay? Now, another thing about ionic compounds is that some of them are brightly colored. Those bright colors are properties of the metal. Okay, so typically, ionic compounds that contain nickel are green. Ionic compounds that contain copper are blue. And ionic compounds that contain cobalt are red to pink, okay, in color. All right, and that's listed here on the next slide. Okay, so copper compounds are blue, nickel compounds are green, cobalt containing compounds are pink, Okay? Sometimes lead compounds are yellow. Okay? Lead is not going to be one of your unknowns on Monday, so we don't need to worry about that for now. So, if one of my unknowns was a blue crystalline solid that dissolved easily in water and whose solution conducted electricity, would it be a safe bet that it probably contains copper? It would be. Okay? And then I would look at my list of unknowns and see if any of them are copper-containing compounds. Spoiler alert, one of them is. Okay? And that would be one of the ways you could identify. Okay? It's ionic, it's blue, okay, it's probably copper. Okay? Or probably contains copper, would be copper, containing copper. Okay? Same with nickel, same with cobalt. Okay? If I had a red or pink crystalline solid that dissolved easily in water, whose solution conducted electricity, it would be an ionic compound, probably containing cobalt, and I'd be looking for something in my list of identities that contained cobalt to be that material. Okay, so everyone kind of understand the process we're going to be going through? Okay. All right, now molecular compounds are quite a bit different. They can be solids, liquids, or gases at room temperature because they have very low melting points. Okay, water is a molecular compound. Its melting point is 0 degrees Celsius. Okay, butter is a molecular compound. It'll melt in your hand. Okay? Its melting point is around like 32 degrees. Alcohol. Okay? Alcohol's melting point is minus 50 or something like that. That's why we use it in thermometers. Okay? We used to use mercury in thermometers, but we stopped doing that for 2 reasons. Why? It's poisonous. Yeah, it's really bad. And secondly, in Canada, there are many times of the year where it's completely useless because mercury turns to a solid at minus 40. And sometimes we need to know what the temperature is when it's colder than that. And once mercury solidifies, it doesn't work in a thermometer anymore. Okay? So it doesn't work here. So we use the red methyl alcohol, okay, that has a much lower melting point and so stays fluid inside a thermometer for longer. All right, so molecular compounds, solids, liquids, or gases. So if I've got a bunch of unknowns on the front table and they're a liquid, any one of them are a liquid, what do I know about that automatically? If it's a liquid, it's not what? It's not ionic. Okay? All ionic compounds are crystalline solids at room temperature. So any unknown that's not a solid is automatically a molecular compound. That would eliminate a lot of compounds from your list of unknowns. Okay? You know it's nothing that starts with a metal. Okay? You know it's none of the ionic compounds on your list because it's a liquid. Okay? And ionic compounds aren't liquids at room temperature. Okay, molecular compounds are not usually as soluble as ionic compounds. Okay, not usually. That's not a great rule because lots of molecular compounds are soluble. Sugar is soluble. Alcohol is soluble. Okay, and there are some things that aren't, like butter, oil. Okay, those are molecular compounds. If you pour them in water, they float to the top. Okay, they're not soluble. They won't dissolve. Okay, now, is it possible for one liquid to dissolve in another liquid? 100% it is. Okay, that's what happens with alcohol. Okay, it's how like mixed drinks are made. Not that you know anything about that because you're very young and have never done that. Okay, but that is how they are made. Okay, you have alcohol and you have another liquid, and if you pour them in, they mix together. Okay, alcohol is soluble in water. Okay, very rarely do you ever get anything that's pure alcohol to drink because it would taste terrible. Okay, and secondly, it would be very bad, okay, for you because it just would be. Okay? But most types of alcohol still have a fair amount of water in it. Okay? Even hard alcohols are usually around 40%. Okay? So they're still mostly water, and they're really just a solution of the alcohol and whatever other stuff was used to ferment it, okay, and the water itself. Okay, does that make sense? All right. Now, the big thing about them, the big difference, we already said, the main difference that'll always tell you it's molecular versus ionic is that their solutions will not conduct electricity. So even if they do dissolve, they won't conduct electricity. So again, a solution of sugar water is going to be non-conductive. Okay? A solution of alcohol in water is going to be non-conductive because there will be no dissociation and no formation of charged particles. So an ionic compound is a series of positives and negatives, like you see on the left here. Okay, a molecular compound are simply chunks of matter that do not separate. Okay, so there'll be no charged particles. Right? The other thing about molecular compounds, they're almost all clear. Okay, there are no bright colors. Okay, for any normal or molecular compounds. Right? So they typically are soluble. The ones which are soluble are going to typically be clear. Okay, if we put sugar in water, it's clear. Put alcohol in water, it stays clear. It doesn't change to pink or blue or whatever else. All right, questions so far? Okay. Now, acids and bases are the next thing we need to look at. We are only going to look at strong acids and strong bases. We're not going to look at weak acids and weak bases. Okay? A weak acid would be like citric acid. Okay? That would be a weak acid. We're going to look at only strong acids, which are ionic compounds that have hydrogen acting as the metal. Okay? So all acids are all strong acids are ionic compounds with hydrogen acting as a metal. Okay. Okay, so acids are ionic compounds, and so they're going to be crystalline solids at room temperature. They are highly soluble in water. Okay. In fact, they're so soluble in water that they dissolve so quickly, they typically make the solution get very hot. You actually have to be very careful if you are diluting an acid. Okay, so when I make the solutions for this lab, okay, I always add pure acid to water, and never the other way around. Okay, because if I do that, if I add water to acid instead of the other way, the material will get so hot that it will break the glass. Okay, it'll just try to expand too quickly. Right? When you do this lab and you're doing your solubility test, okay, seeing whether something dissolves or not by adding water, you'll be using this device. It's called a thermometer. You probably don't pronounce it that way. Okay? Pretty simple to use, but I want to have this in my solution when I'm making it, because if I see the temperature go up or down, that could be indicative of either a strong acid or a strong base. Okay, everybody with me there? What's the little red thing for? Okay. What a lot of people do is they think it's like a marker and they move it to where they want the temperature to be, and then they realize that all that does is make it impossible to read the temperature wherever they put it. Okay, so that's not actually what it's for. What it's for is for you to hold on to, so that your fingers don't warm up the thermometer. Because if I hold the thermometer like this, the warmth of my hand will make the temperature go up. Okay? I don't want that to interfere with my results, so I hold it by the little red plastic thing. Okay? If my thermometer doesn't have the little red plastic thing, do your best to hold it by the top as much as possible. Okay? Okay, now we already said there are going to be no taste tests. But typically, acids taste sour or tart. Okay, think of citric acid. Right? If you have a lemon or a lime, okay, something that has a lot of citric acid in it, it's typically sour. Okay, vinegar, kind of a sour taste. Okay, typically acids have that type of vinegar-like smell, okay? So if you're doing a smell test, which is one of the tests you can do, okay? If something smells kind of like vinegar, it's likely to be a strong acid. Kind of gives you that curling the hairs in your nose sensation, okay? That's definitely going to be indicative of a strong acid, okay? And they'll turn your litmus indicator to acidic colors. So what you'll be using for that test is Hydrion paper. Okay, inside the tube are pieces of Hydrion paper. Okay, so you just tear one off, then usually tear it in half. One piece can usually test 2 solutions. Dip it in the solution and then compare it to the color chart on the outside of the tube. Okay, whatever color matches, that's the pH of your solution. Now, for almost all of your materials, they're going to be within the range from 5 to 9. Okay, they're all going to be around neutral. There's going to be one that's going to be wicked acidic and another one that's going to be wicked basic, and everything else is basically going to be in the middle. All right, so you're really only needing this test for 2 of your materials. You'll have one strong acid and one strong base in the unknowns. All right, so all acids, all strong acids, have hydrogen acting as the metal. So this is a strong acid. Okay, that's hydrogen chloride or hydrochloric acid. Okay, it's actually the stuff that's part of your stomach acid. Okay. Now, which would be stronger? This or that? Which would be the stronger acid? If we're looking at this logic right here, what makes something acidic is the H+. Which one of these would be stronger?
The first one?
Nope. The second one, because it can give up more H+. How many H's does it have? 2, right? So when this hits water and dissolves, it's going to break up into 2 hydrogen plus ions and 1 sulfur ion. Okay? That means it's going to contribute more H+ to the solution, which will cause it to be more acidic. Okay? So the more hydrogens something can give, the stronger it will be. Okay? That is nitric acid. Okay? Nitric acid is so acidic that you actually have to be careful not to get the fumes on your skin. Okay? If you get even the fumes of nitric acid on your skin, you will have chemical burns in a matter of hours. Okay? You won't even notice that it's happened until later when your skin starts to blister. Okay? And badly. Like it's nasty, nasty stuff. All right. Does everyone kind of get the idea there? So if I've got an unknown compound in my list of unknowns, it's a white crystalline solid, dissolves easily in water and the temperature goes up, okay? Solution conducts electricity, and it has a pH of 2, okay? Would I be looking for something in my list of unknowns that starts with hydrogen? What do you think? I would be, because it's a strong acid, and all strong acids have hydrogen acting as their metal in an ionic compound. Okay? So again, this is the process that we need to go through on Monday. Okay, now, bases are the opposite. They're still an ionic compound, but instead of having all the acidic properties, they obviously have all the basic properties. And what makes something a base is the presence of hydroxide, okay? That polyatomic ion that's in our chart. So if something is an ionic compound, and it can give up OH ions when it's dissolved in solution, it will be a strong base. Okay? If you've ever watched any like crime shows or Like they got that investigation Discovery Channel, my wife loves it, but it's like all murder. It's all how people try to get away with it and all that. Okay, and they almost inevitably, if they're trying to get rid of a body, they put lye on it. Okay, lye contains a lot of hydroxide, and so it dissolves the body. I'm not trying to tell you how to dispose of the body, but this is like a chemistry thing. Okay, so we've got bases can obviously dissolve things just as easily as acids can. Okay, so any ionic compound that's going to contain hydroxide is going to be a strong base. So here would be one. This is what's that's in lye, sodium hydroxide. It's also an oven cleaner. Right, so if you've ever used the white foaming stuff to clean the inside of your oven, that's what's in it. It has a very distinctive smell, actually, okay? And it's caustic. Like if you inhale it, you can feel it burn your lungs. Okay, it's nasty, nasty stuff. So that's why it always says on the oven cleaner can, using a well-ventilated area, it means don't stick your head in the oven while you're spraying it. Okay, because if you inhale that, it'll be caustic on your lungs. Okay, so anything that can give up OH is going to be a strong base. The more OHs it can give up, the stronger it's going to be. Now, it does have to be an ionic compound. Okay? And I only say that because one of your unknowns looks like that. Is that going to be a strong base? No, because it's what kind of compound? It's molecular. Okay? Even though it has OH in it, it actually doesn't have hydroxide per se in it, because when this dissolves in solution, it doesn't break up. So it doesn't release this OH. It may contain it, but it doesn't release it, which means it doesn't make the solution more basic. Okay? In fact, this is ethyl alcohol. It's the alcohol that is in all alcoholic drinks, okay, and hand sanitizer. Ethyl alcohol. Right? But it's not a strong base because it's a molecular compound, not an ionic compound. So it's got to be an ionic compound if it's going to be a strong base. Okay, so typically bases taste bitter. Okay, again, we're not doing any taste tests, but if you ever accidentally got soap in your mouth, okay, soap contains lye, which contains this, okay, which is why soap is really bitter. Okay, if you've ever tasted baking soda by itself, baking soda is a weak base, but it's very bitter. Okay? So anything that tastes really, really bitter is a base. All right. Questions on bases? Right? So the other things they're going to do all the same things other ionic compounds do. They're going to be they're going to be crystalline solids at room temperature. They're going to dissolve very easily in water. Their solutions are likely to get hotter. Okay? And obviously they're going to conduct electricity very well, and they're going to have a pH of higher than 7. Okay? And the one in our lab is going to have a pH of 14. Okay? I mix everything uber strong, okay, so that the results are obvious. Okay, questions there? All right. Okay. I'm going to give you about a 5-minute break here. Let's actually even say 6 minutes. So at 9:40, we're going to regroup here, and we're going to go over some of the tests that you're going to need to run in the lab. These you're going to have to write down because they're not in the notes. Right? Okay, so when we do this lab, okay, we want to be able to use as many physical properties as possible for each material to help us figure out what its identity is, right? Because we're just going to have this list of materials, okay, and we know that, one of them is material A and one of them is material D and whatever. We just got to figure out, was A water and was D hydrogen chloride? We've got to figure that out. Okay, so we want to record and observe as many properties of each material as possible. Okay? We're only running a few tests, but we can get a lot of physical properties out of those few tests. Okay? Now, the first and most important test we want to run actually gives us the most physical properties that we can get, and it's the simplest test. There's a whole bunch of unknowns at the front of the room. What should you do with all of it? What?
Test it if it can conduct electricity.
Even before that, that is going to be one of the tests I'm going to want to run for sure, because that tells me definitely whether it's ionic or molecular, so that's an important test. I just don't want to do it first, because in order to do that test, it already has to be dissolved in water. And dissolving it in water isn't my first test either. Okay? What do I want to do with all these materials before I start mixing them with anything?
Smell.
Yeah, smell is one of them. Okay? Now, when you smell an unknown material, is there a proper technique for that?
Yes.
Yes. Okay? And it is not, okay? Because for a couple of those unknown compounds, if you do that, you will be flat on your butt, bleeding from the nose. Okay? All right? And I only say that because it's happened to me. It's not because I snorted it on purpose. It's because I had a cold while I was mixing it, and I sneezed, and then you know what you do right after you sneeze? You inhale sharply, and I was right over top of the strong acid. Okay? When that happened, yeah, no, not cool. Okay? Yeah, you thought like the brain swab test for COVID was bad? Yeah, it's way worse than that. Okay? So we want to be careful. You want to make sure that you waft the material. So hold it, you know, about out here, not right under your nose, and just do this. And if it's got a smell, you'll smell it at that range. If you can't smell it at that range, its smell is not important. Okay? There's only like really one whose smell is important. Okay? After that. So smell is one. What else do I want to do? Look at the color. What else? Can I tell a lot of the properties by just going up and looking at it? Yeah. Okay. I'm going to get, I mean, the smell I get by smelling it, but I'm up there looking at it. Okay. Color I get by looking at it. Okay. Its texture is another one, right? And I'm not saying like touch it with your fingers, because obviously I wouldn't want you to do that. Okay. But you can take the scoop, okay, and just kind of, you know, scoop it a little bit and see, is it really grainy? Or is it sticky? Okay, is it crystalline or is it waxy? Okay, things like that. Those are all important observations to make, okay, because they tell us a lot about it. If it's not a crystalline solid, then it's not an ionic compound. Okay, and you're going to have a couple of unknowns that are solids, but they're not crystalline. Okay, so those are going to be important. The shape of the crystals could also be important. Okay, some of them are going to have really big crystals that are circular. Okay? And some are going to have really tiny, like shard-like crystals, and some are going to have really tiny cube-like crystals. So those are all going to be important observations to make. Okay? The state, is it solid, liquid, or gas? We're not testing any gases. They're inherently difficult to keep in a beaker. Okay? So we won't have to worry about any of them being gases, but there's definitely going to be solids and liquids. State's going to be important. Okay? These are all observable properties that can tell us a lot. If I've got something and I walk up there and it's a red crystalline solid, I got a pretty good idea what it is already. Okay? If I've got something on my list that's an ionic compound containing cobalt, that's probably what it is. Okay? Just looking at its color and its texture can pretty much do all the work for me. Okay? Everyone following me there? Okay. So the first test that you're going to run is very simply the observable properties test. These are the properties that you can observe without having to do anything but really go up there and look at it. Okay? So things we want to observe would be color, probably the most important one. Okay? State of matter. Is it solid, liquid, or gas? Like I said, there are no gases. Okay? The nature of the matter. Is it crystalline? Is it cloudy or clear? Okay? Is it waxy? Is it hard? Is it oily or like more liquid? Okay, viscosity is another physical property. Okay, an odor test. Does it have a smell? If I've got a clear liquid that smells like hand sanitizer, it's a pretty good bet it's got alcohol in it. Okay, that could be an easy one. So the odor test could be important. Okay, so those would be the first tests that we would run. Okay, because once we do our second test, we can't do these tests again, unless we go back up and look at the main samples. Okay, but our sample back in our table will be done, okay, after the next test. So incidentally, at your table, you will have what is often referred to as a depression plate or a spot plate. Okay, and it's simply going to have 6 depressions in it. Okay, so you'll be able to test half of the materials at one time. Okay, so you'll put enough in here to, kind of cover the bottom. Okay, you really don't need much more than that. If you heap it full, it's going to be really hard to do the solubility test because there'll be no room for the water. Okay, so cover the bottom with the unknown material. Okay, do your observable properties test, with the exception of the odor test. Why do you not want to do the odor test with all 6 of these full? Not so much, well, I mean, you might, but the other problem is, how do you know which one it is? Like, they're all right beside each other. You're doing this, who knows which one you're smelling? Okay, so the smell test is going to have to be done on the main samples at the front of the room. Okay, and we do have to be a bit careful with that, obviously being COVID, and okay, you're going to send one group member up and they're going to pull down their mask and do the wafting test and then put the mask back up. Okay. Yeah, it sucks, but that's the way we gotta do it. Okay, so you'll have a depression plate and you'll have the stuff in there. Okay, once we've done the observable properties, then the next thing to do is see whether it dissolves in water. Now, are you going to have a lot of water in here? Okay, so if you cover the bottom of this with anything, even if it's really, really soluble, what's the likelihood you're going to get it all to dissolve in that much water? Think highly likely or less than likely? Yeah, I'd say less than likely. Even for a really soluble material, you're probably not going to get it all to dissolve in this amount of fluid. So how do you know if something is dissolving, even if it doesn't all dissolve? If I put blue crystals in here, what would be a sign when I add water that it's dissolving? Yeah, the solution turns blue. Okay, if I've got a colored material and when I add water to it, the water changes color, it's because the material is dissolving in the water. Okay, that would be one sign. Okay, another sign to look for would be, look at the material itself. Is it shrinking, changing shape? Okay, that's always a sign that something is dissolving. Okay, like you might have obviously less of it than when it was in there dry. Okay, that's a sign that it's dissolving. And another thing you're going to be watching while you're doing this is a temperature change. Okay, so while you're doing the solubility test, you have to have the thermometer in the material while you're adding the water. Okay, if there's a temperature change, then it's definitely dissolving. Okay, and that can be up or down. You're gonna have one material that you're gonna test that's actually gonna make the temperature go down. It's gonna make it get colder. Okay, you shouldn't get any change in odor. Okay, none of these should smell bad as a result of adding water. If they smell bad to begin with, they're still going to smell bad, but there should be no new smells as a result of adding water. Okay, but definitely temperature change, color change, okay, and the look of the material. Okay, if the material just right away floats on top and basically does nothing, is it dissolving? No. Okay, like if you had like coconut oil, okay, or something like that in there, and you added water to it, it would just float on top and do nothing. Okay, that's not soluble, right? But if I pour water into it and they mix together and I can't see any visible parts, then it's soluble. Okay, those are all the signs we want to look for. Now, once I've made a solution, now I can check to see if the solution conducts electricity. Okay? That whole conductivity test only applies to the material's solution. So my next test, okay, is my aqueous conductivity test. And that's where I stick the conductivity tester leads into the material, okay, and see whether or not it conducts electricity. What would I want to make sure I do between every single test?
Like clean.
Yeah. Okay. You have to make sure you rinse the thermometer, the stirring rod, okay, which you'll get, it's just a glass rod, okay, and the conductivity tester. If you don't, you're going to contaminate your other solutions, okay, because you're going to bring the conductivity tester, which is still going to have some of those ions or solution on it, and stick it in the next one. If that one if you do that, and you had one that was conductive, and the one you just put it in was supposed to not be, it's going to show that it is, and you're not going to have good data. So what you'll do between each test is rinse it with distilled water. So you'll have a little squeeze bottle, okay, that has distilled water in it, and you just give it a little spray over the sink, okay, so that it's cleaned off. So you're not bringing any ions with you from one sample to the next. Okay, so it'll be really important to rinse them off between tests. Okay, so you're going to look for the lights, rinse in between. What test should I do last? I showed you how you would do it. It involved this little vial.
How acidic it is?
pH test. Okay? The reason I do this last, once I stick a piece of pH paper in the solution, I chemically change it. This is a chemical reaction that happens here. Okay? Changing the color of the pH paper is a chemical reaction, and I no longer have a pure sample of the original material. I can't do any more tests after the pH test. So the pH test is pretty simple. Okay? You just put the strip in there, and then you compare the color to the chart. So those are the 4 tests we're going to run. So tomorrow, I'm going to go over lab report format and expectations. Okay, I'll give you, I'll put a sheet on Google Classroom that you guys will follow along with tomorrow. Okay, so you can see kind of what the expectations are. Thursday, we're going to start the pre-lab stuff. So we're going to work on how we write our variables, how we write our hypothesis. Don't pack up yet. Okay, how we write our hypothesis, get started on writing the procedure. Okay, because you guys are going to have to describe how these tests are going to be performed or something. Okay? And then, on Friday, we'll have some time to kind of finish up naming and probably talk a little bit about solubility. Monday, we'll do the lab. Okay, so that's the plan for the next week or so. Okay. Any questions on what we're doing? Now, I'll get you to pack up and get everything off your desks so I can come around and wipe them down.